Hello everybody, my name is Irio Lavagno from Tiber Lab Rome, and I'm going to talk about our contribution to the Challenges project, which is about metadata extraction, manipulation, and data storage. So I'm going to use a few slides to introduce the problem, then I will go deeper into each part. As you know, produce a lot of data, and along with those data comes metadata, mostly about instrument configurations and so on. So we need some system to store this data, and especially to be able to retrieve those data in a meaningful way and in a efficient and comfortable way. So one thing we thought using is HDF5, as I believe many of you know what HDF5 is. The name stands for hierarchical data format. It's a data storage system. It's open source, it's cross-platform, and allows for easy sharing of data because it stores everything in a single file. It's quite fast and allows also to store metadata along with data. In HDF5, data is represented mostly as multi-dimensional vectors. And metadata can be anything from strings, numbers, objects, complex objects, and so on and so forth. HDF5 is mostly a set of libraries offering functions to manipulate data metadata. One of its advantages is that it has interfaces coupling different many programming languages, so it's very versatile. And as I said before, data within the HDF5 structures are represented as multidimensional vectors, vectors in computer science sense and not in physics sense. And it's hierarchical, so it allows to build a tree-like structure in within the data sets, allowing it to group files, group data, what it calls data sets, group them as you would group files within a directory on a file system. We'll come back again later to this similarity between the inner structure of HDF5 and a file system, because we exploited it to allow for a practical interface towards the system. One of the limitations of HDF5 is that the interface towards querying the metadata is quite limited. You can just store them as a set of key value things, where value can be a complex object, but it's still just like a dictionary, accessible only by its name. So one of the improvement we thought adding is add a SQL database, a relational database, uh, where to store metadata instead of the standard system offered by HDF5, which allows for more complex queries and a more sophisticated way to access metadata, group them, sort them, and so on and so forth. So we used one of the features of HDF5, which is plugins. It allows to add plugins which take over the standard way of doing things and allow to implement things in different way. So we use what it's called VOL plugin, which allows to intercept all the calls that to manipulate metadata and redirect them to a different model. So we added a SQLite database for this purpose. SQLite, as you may know, is an open source database. It's again very light, hence the name. It stores data mostly in a single file as well, and it's very optimized. So it's fast and efficient. One of the other problems to address is that metadata come in different formats and different shape, because most of the instruments have proprietary output files, and they call the same object in different ways. They use different formats, and so on and so forth. So we thought of adding again a pluggable normalizing structure where you can add preprocessors to the data metadata, which have the purpose to normalize the data and make them compliant with the Charisma guidelines. As I said, there is strong similarity between the inner structure of the HDF5 and a file system on disk. Similarity that it's intentional, of course. Um, and this can be exploited to actually use a virtual file system to manipulate the data within the HDF5 structure itself. So, for example, we can simply copy a file into the virtual directory and have it inserted into the the HTTP5 tree, or maybe using the create directory command to create a group within the structure of the HTTP5 tree, and so on and so forth. We can delete files, move files from within a group to the other, and etc. So one of the things we added is actually a virtual file system, which is quite a common thing in Unix, in Linux, but it's available as well in Windows, at least under WSL. I'm quite sure it's available also in native Windows, though I'm not sure how it's implemented. Um, in Linux, it's quite easy to create a virtual file system because there's a common library called Fuse, which stands for File System Users in User Space, which is designed to make a user able to create a virtual file system without having to write an actual device driver, so having something that has to run in kernel mode. Everything works in user mode, so it's easy to deploy. It doesn't need special uh, permissions or whatever. So it's very common, very useful. We added a fuse file system to the project, and I will show you some of the features. Okay, now let's
One
get
other thing
a bit more
we
technical
added is
and start
a REST
looking
API,
at the code.
which will allow to
As I
add
said,
external
the whole project
applications
was a proof of concept, so it
to
was meant
offer
just to
different
prove that
user interfaces to
the
the data.
idea
For
can work.
example, a web
It
application
actually works.
which would allow to
It's usable, but
have the
of
storage
course, it would
system
take a lot of
running on a server,
work
maybe a cloud
to
server or something,
to
and
clean up the
have
code and
the data
to
metadata
optimize things
accessible
and
from
so
remote
on and so forth.
sites.
So
And
you will
also
forgive
will
me
allow
if
to
some
add
parts of the code
authentication and
look
authorization
ugly, but
filters
that's
so that you
that's
can
how
give
it comes
access
out
just
when
as
you have to experiment a lot
under
and you don't have time
identification
to
and
clean
so
up the
on.
code afterwards.
And
Okay,
being
now let's get
absolutely general,
a bit more
REST API
technical
offer
and start
a very common
looking
interface
at the
to
code.
add almost anything to
As
the
I
system,
said,
whatever
the whole
interface you
project
want
was
to
proof of
create
concept,
towards the
so it
data,
was meant
either
just to prove that
human
the idea can work.
interface or
It actually
machine
works.
interface to allow to from
It's
external
usable, but
processes to
of course,
access and
it would take a lot of
extract and manipulate the data.
work
It's possible.
to clean up. Okay, now let's get a bit more technical and start looking at the code. As I said, the whole project was proof of concept, so it was meant just to prove that the idea can work. It actually works. It's usable, but of course, it would take a lot of work to clean up the code and to optimize things and so on and so forth. So you will forgive me if some parts of the code look ugly, but that's how it comes out when you have to experiment a lot and you don't have time to clean up the code afterwards. The code is divided in substantially in two parts. The actual Vol plugin, which is implemented using the HDF5 toolkit, which is simply a set of examples and description files that allow you help you to create plugins. And it's a simple C++ project with a few files and a make file and so on. We are going to have a look at the code and see how it's implemented. The other part is written in Java. This is just because I'm much more familiar with the Java language and I didn't have time to implement everything in C++. That would take me more time, so I decided to take a shortcut and encode that part in Java. So the whole virtual file system and the pluggable preprocessors are written in Java. So we will have a look at that as well. As I said, HDF5 has libraries to interfaces and libraries to work with many languages. So having a part written in C and a part written in Java is not a problem. It would be, of course, a better engineering choice to uniform the languages, but it's something that can be done in the future. Uh, I was thinking that an actual pretty interesting exercise would be to recode everything in Rust because it's a very interesting language and has many advantages. Of course, it would take an experienced Rust programmer, which I'm not. So it's just one of the wishful thinking. Maybe someone will take over the project and convert it. I don't know. So far, it remains as it is. Okay, sorry if I will be looking askew, but I have another monitor here with the codes, so I need to look on the left side. Um, okay, so this is the VOL plugin. As I said, is just a simple C++ project with configure makefile and all that the usual jazz. The sources are of course under SRC, and there's not much stuff as you can see. There's the the SQL part, which is the part interfacing with the SQLite library. Um, with the main functions, which the first one creates the database if it does not exist. There are functions that create attributes, um, list attributes, open attributes, and so on. There is just one thing worth noticing, that there is an add dataset function, which is not really it just adds a placeholder within the DB, because we need a joining table between the actual HTF5 dataset, which is an object within the HDF5 structure, and the attributes that are in the DB. So this is a table with which holds simply the two IDs, the internal ID from HDFI, which is a long integer, and the ID, the key value in the attribute table in the SQLite file. The actual plugin is this one, which is a bit more complex. Um, okay, the main thing here is this structure, which holds the function pointers to all the callbacks that are called by the HDF5 system whenever any operation it's executed. Um, this covers many actions. As you can see, we are using just a part of them. Um, the ones that are left with null values are simply called the default operation. Um, the ones you fill with your own function pointer will call your function before or instead the default function, depending on what you return. You may decide that you want to fall back after what your operations you want the default operations being executed anyway, or simply return to the system from within your function without calling the default one. Um, as I said, we implemented just some of these, and the ones that we are interested in are uh, mainly the ones accessing the attributes. Attribute is the name that HDF5 gives to metadata. So you can attach attributes to the objects within HDF5, and that will be the actual metadata attached to the objects. The attributes, as I said earlier, are just things, objects, which can be many different things. Strings, integers, arrays of integers, and whatever, or even complex objects, and they just have a name, so they can be retrieved usually just with their name. Here are some utility functions. We can see for example, the attribute create, which is one of the functions we override from the default one. And as you can see, this one is going to call the one of the functions we saw in the previous file, which creates the attribute in the database. All the code that's above is needed to retrieve information about either the object the attribute will be attached to, and other information about the type and stuff like that. Sorry for the beeping, but it's the air quality sensor in my room that's actually telling me that I'm dead. I hope it is wrong. I believe it's malfunctioning for some reason. So this creates the attribute within the database, and then registers the pointer to the attribute within the HDF5 structure, so that it can be used as a normal attribute within the system. Of course, there are similar functions for all the other operations on the attributes, but the, the mechanism is the same. Compiling the plugin is quite trivial. As you can see, there's a lot of warnings because the code is not as clean as it should be, but it compiled, it generated the challenges SQL function .lo, which is a shared library in the Linux system, which gets loaded by HDF5 when it starts, if it gets placed in the actual right place, which is this one. So it's enough to copy the library in that directory, and when the HDF5 is started, it loads the plugin and actually intercepts the function, redirecting them to the plugin itself. Now let's have a look to the other part, the Java implementation of the virtual file system and the pre-processing part. Okay, so this is a typical structure of a Java project. As you can see, it's divided in three different packages, four different packages. The HDF5 fuse is the actual implementation of the file system. The REST API is the implementation of the REST API. We are going to look into that as well. And data contains the data structures and the preprocessor and data information for the processing of the instrument files. At the moment, I implemented just one preprocessor from one data format, which is the WDF file from WeTech. Of course, the interface to implement the preprocessor is general, so you can anybody can implement a different an additional data format and add it to the system. The preprocessor will recognize the form, the actually not the format, but the extension of the file. It's based on the extension. It's possible to implement a different meaning to recognize the file types, but at the moment it just recognizes them by extensions. So if it finds .wdf, it knows that that preprocessor is the one that manages that kind of file. Let's now have a look at the REST API. As you can see here, there's a little bit more things, but the main thing is this one. These uses the default HTTP server that's available within the Java system itself, the Java libraries that come from with the language. So it just creates different endpoints for the different calls. Creates the handles, the handlers for the different functions, and we can have a look at just one of the handlers, and the others are mostly very similar. So let's have a look to the create. Just the create is not implemented, of course. Okay, let's see another one. Okay, this one is implemented. This calls the HDF5 interface, gets the meta information, so the metadata of a certain path, and creates a structure. Yeah, it's the output is an hash map of objects, and it gets then serialized as a JSON object somewhere somewhere I don't remember where. Anyway, it gets just trust me. It gets turned process serialized as a JSON object and returned to the caller. The implementation of the virtual file system is quite straightforward. It's just an implementation of the standard Java interface to the Fuse file systems. Um, it's the structure is taken from an example that comes from the HDF5 itself, from Fuse itself. Sorry. It works mainly as it works the HDF5. You implement a series of callbacks that the system calls when it needs to do operation on the file system, and if you implemented those, they get called and do things. As you can see, many of them are not actually implemented because I didn't need them. For example, I have no need to create symbolic links or hard links to the files. I didn't implement the rename function because it wasn't very important. It can be implemented in the future. As well, I didn't implement the changing of permissions of the files. This can be implemented, but it was not necessary to the demo, to the proof of concept. Um, the important ones is the get attribute, which gets called quite often from every operation in the file system. So it's quite important. Um, then there is the read directory. So this is actually called when you call ls on the directory, on the virtual directory, and goes to this one goes to the HDF5 um, library and calls at least directory. We are going to see this in another Java part, which is the one that interacts with the HDF5 system. So this is quite a normal implementation of the file system itself, except uh, for the create file itself, or the flash, the create, I think it is. No, it's not here. Okay, so we will see it in the other source. Okay, here it is, the interface towards the HDF file system. You can see here the list directory method that we just saw in the other code in the other source from the read directory method of the Fuse file system. This interacts with the HDF5 system, and this gets the root group, which is always present in the HDF5 system, and lists all the objects within that group, and creates a structure which is more substantially a list of objects that gets returned to the fuse part, which will then show return to the operating system to be shown to the user. So we have all the other functions that implement all the other operations. Here, the create dataset is actually creating a dataset in the HDF5 system, because when you copy a file within the file system, the file gets preprocessed, and then a dataset is created into the HDF5 system. So we have here we have all the opening, closing, writing, reading operations for the data sets, and the same for the attributes. Um, Here we have also the function, the methods that I have to find it because I don't remember exactly what it is, where it is. This process file, it's what gets called when a file is inserted into the file system. The file processor class is here. Is the one. This is just an interface. Actually, I need to find who implements it. UDF file processor, just right. Okay. I'm sorry, but I don't really remember everything by heart. Okay. This is called when a file is inserted, it recognizes, it calls this, handle this, that decides if he needs to handle this kind of file or not, and it, I lied there earlier. I said that it recognized the file by extension, but it actually does a more clever thing, because it looks for the signature within the file. The WDF files have a 2-byte signature in at the beginning of the file. I don't remember the numbers, but it's no, it's actually string. It's 4 characters, and it's WDF and the version of the file. So if it finds the signature, then decides that it needs to process this file, and returns true. Otherwise, it returns false, and the HDF5 interface goes to the next processor, asking it if it's able to process that kind of file. Uh, Here, the process is quite complicated. It reads the header. The header contains a lot of information about the file, which parts are present, which parts are not, and then it goes to process the single the specific parts. Already on this in this part, it creates HDF5 attributes because this part, the header file, already contains metadata information, but then there are also subparts that contains further informations, and so the structure goes on to parse the whole file. At the end of the WDF file, there is the actual data sets, which get inserted into the okay, now I remember. I didn't do that yet, so this preprocessor just extracts the metadata and creates the attributes, but then stores the whole WDF file as a data set in HDF5. There should be a part that extracts the actual uh, data from the file and stores them as a data set, but I didn't have time to implement that. So this is not a complete parsification of the file. Um, Most of them are implemented, not all are implemented. I don't. I honestly don't remember if I implemented the file upload. I see that I implemented the file uploader, but I'm not sure. Yes, it's implemented. Here it is. To the API and upload it to the HDF5 structure. Um, okay. Of course, this can be extended I don't remember again if I implemented the authentication part. No, I didn't. I didn't do any authentication or authorization implementation, which would need to be implemented, of course, if this thing gets published on the internet. Um, I also created a very ugly web interface, which is not here. I will have to look where it is, and I will add another part to the video showing that it was very ugly, but it can show what it means to implement a simple web interface using the REST APIs. Okay, let's go to the conclusions. Since, as you can see, the light is going away and I'm pretty tired, so I better finish this thing. So, in conclusion, we saw that the whole idea of adding a SQLite, a SQL interface to manage the attributes in HDF5 is possible. It works, and it just needs to be implemented in a more engineered way. There are a lot of things that can be done in a better way, and a lot of things that can be added as well. For example, one thing that should be improved is that, as I mentioned in the beginning, HDF5 has the advantage of storing everything in a single file, which makes it very easy to share and to move and to backup and whatever. And so adding a second file which contains the SQLite DB is not the best way to do it. So one of the improvements that can be made is actually store the SQLite database as a data set within the HDF5 structure, which is possible. It just needs to be implemented. Another thing that can be done is adding the ability to do SQL queries to the actual data, not just the metadata. Also implement the possibility to add preprocessor to the data themselves. So if we need to normalize data to have them adapted to the same parameters or whatever, it can be done. Or maybe add filters to the data, so extract all the data that match certain requisites. Um, Another thing that again is wishful thinking, but we could add a vector database and add an LLM system to that would allow us to mm, interact with the data with data and metadata with natural language, so we could ask questions to our metadata and data and get answers in different formats created automatically for us, and well, many other things that one can think of. Um, as I said, this was a proof of concept. Anything can be done starting from here. So I will put the whole thing on GitHub. I'm adding the references here in a final slide in the video. Also, if you have any questions or comments about it, you can. I will leave you. I will leave here my email address, so you can just send me emails, and I will try to answer as best as I can. And so that's it, I think. Thanks for watching, and have a nice evening, day, or morning, whatever the time is when you are watching this. I'm just going to show you a small demo of the whole system. I created a virtual machine containing all the necessary things. Okay, here we are in the same directory we saw before, just recreated within the virtual machine. So I'm just going to check that everything is okay. Okay, so um, this directory here, the mount point, is where The virtual file system will be mounted, and I'm going to split the screen in two so that you can see. Well, I can just create this in another tab and go to the same machine. Okay. So here we start the system, the HDF5 with all the add-ons. It's very verbose, as you can see. So now, as you can see, the mount point has this meta directory, which is virtually created by the system. It doesn't contain anything, it's just a placeholder. So I can create a subdirectory within the mount point. And as you can see here, it created okay, well, we have some errors, but it's not a problem. Anyway, it created the group test. So we have the test group, and I can copy a sample file inside the test group, and it will start parsing the file and extracting all the informations. It's finished. So now if I see what's inside the test group, there is the WDF file that I just copied, which, as I said, it will need to be actually extracted. I mean, the data will need to be extracted, and so instead of the WDF file, we will need just to have something containing the data vectors. And we have this virtual file, which is meta, which is uh, a JSON file created from the metadata defined in the file. So what happened here is that I copied the file within the virtual directory, and it got processed. Metadata got extracted. They are inserted into the database. We can also have a look to the database, and we have some tables with, for example, we have data sets which contains the file name and attributes, which contains all the metadata extracted from the file with their internal ID. This is actually a HDF5 ID of the object, with a few other parameters. One of these is the ID of the dataset they belong to, and the others I don't. Another one is the type, another one is the size, and so on and so on and so forth. So I'm also going to show you an example of the web interface which is talking to the REST API. That's quite ugly, but I'm going to show you it anyway. So you have an idea. I need to start a Docker. Uh, okay, I made a last minute change to the running script, and of course it doesn't work. Okay, it started the Nginx web web server, which is running a simple web application. I'm going to show you now. Just time to switch the screen I'm sharing. Just a moment. Going to stop the recording and resume it. Okay, here's the web interface. It's very simple. It shows the root, which is the root of the HDF5 file system, actually. And if I expand it, I see the test group with the two files within. And if I click on meta file, it shows the same thing we were seeing in the JSON file, but this one is extracted by calling a REST API on the system. So it gives access, of course, to the same data, but the way it gets retrieved is different. I could actually edit well, no, I was trying to implement the way to edit the data, but it's not yet possible. As I said, this is very rough. It was just to show that it could work. So I think this is all, and so thank you for listening. For watching this, and I'm going to just add the final page with all the addresses you may need to contact me if you're interested. So I will just add my GitHub page and my email address. So if you want, I'm available to answer questions. Thank you all for your patience, and see you.